we would like to solve for z. E to the z equals 1 plus I. So e to the z is e to the x plus iy, which is e to the x times cis y. So this is a polar form, and therefore the best way to approach solving this equation is to write the complex number on the right side in its polar form. So we would like to write 1 plus I as r cis theta, where r is the modulus of the complex number and theta is the argument of the complex number. So r, the modulus of 1 plus I, the modulus of a plus bi, recall, is the square root of a squared plus b squared. And that's the distance from the origin to the complex number. So we have 1 squared plus 1 squared, that's 2. So we have r is the square root of 2. And the argument for that, we need to recognize the location of the number 1 plus I with regard to the first quadrant. We need this angle, which is 45 degrees here, since the y and the x are equal, 1 and 1. So 45 degrees is an argument, which means that theta can be written in radian form, pi over 4 plus 2k pi. There are infinitely many arguments for any complex number, except for 0, which has no arguments. So that was pi over 4 plus 2k pi. So infinitely many angles are coterminal with this 45 degree angle. Okay, so getting back to the equation, e to the z equals 1 plus I. We can write it as e to the x cis y equals, and putting 1 plus I in the polar form, it's square root of 2 cis pi over 4 plus 2k pi. And now we just equate the various parts. E to the x equals the square root of 2, and y equals pi over 4 plus 2k pi, where this k is any integer, positive or negative or 0. So there are infinitely many choices for y, which means that there are infinitely many solutions to the equation. X is the natural log of the square root of 2, which is the same as 1/2 times the log of 2. So there's only one x that will work, but there are infinitely many y's. So all of the z's that work are 1/2 log 2 plus I times pi over 4 plus 2k pi. And we can look at those solutions. The x is 1/2 log 2, and the y, there's infinitely many y's. The first one is pi over 4 times I, that's one solution. The next one is 9 pi over 4 times I, there's another solution. Then there's 17 pi I over 4, that's a 17 there. That's here, and then we have one down here, negative 7 pi I over 4, that's down here, and then another one, negative 15 pi I over 4, that's down here. So all of these complex numbers are solutions to the equation e to the z equals 1 plus I. There are infinitely many of them, and they are spaced apart by 2 pi I on the imaginary axis, because the function e to the z is 2 pi I periodic.